Good morning, students. Welcome to the next class on electric potential and capacitance. Before proceeding further, let me recapitulate what we have discussed so far. The first important concept was on potential difference. The potential difference between 2 points A and B was defined as negative of work done by electrical forces in bringing unit positive charge from point A to point B. If you write electrical forces, you have to put negative sign. If you write the definition in terms of external work done by external agent against the electrical forces, you have to write plus. And these are work per unit charge, so the SI unit will be joule per coulomb, that is also called as volt. And mathematically, if we know the electric field, then we can write delta V as negative integral E dot dr from A to B. This was the most important concept that we have discussed in the beginning of this chapter. Its special case is one when we bring unit positive charge from infinity to some given location. At infinity, we choose the potential to be 0, and that's why this gives the value of potential at some point r. To find a value of potential at some point, you have to use this particular formula, minus integration E dot dr from infinity to that point. Then in the last class we discussed about change in potential energy. So this is potential V, this is potential energy U. Delta U is nothing but the negative amount of the work done by electrical forces to change the configuration of charges from initial configuration to some final configuration. What does that mean? If we have some charge distribution and if the charges are displaced from their positions, in doing so, whatever work is spent by the external agent, that much work is equal to the change in potential energy of the system. If the charges are very far, then we say the potential energy of the system is chosen as 0. So if we have a pair of charges, its potential energy we have derived in the last class is equal to 1 by 4 pi epsilon naught q1 q2 by r. What is the meaning of this statement? It means if you bring the separation, if you change the separation of these two charges from infinity to r, first they will be very far, and then we bring them closer to a separation of r, then we have to do some work. That work is equal to this much, which is nothing but potential energy of this particular charge configuration. Now this is the expression for a pair of charges. If we have 3 charges, there will be 3 pairs. Accordingly, we can write the answer. For 4-point charges, there will be 6 pairs that we have seen in last class. I would like you to revise them first. We have also seen the value for potential due to a point charge. Here we have a point charge at a distance r. The value of potential is given by this formula, 1 upon 4 pi epsilon naught times that charge by that particular distance. Both of these V and U, or delta V and delta U, are scalar quantities. One more thing we have discussed, that if there are 2 points, say A and B, and a point charge Q is taken from first point A to the second point B, then in taking this charge from one point to the other, the external work that needs to be done is equal to the product of that charge Q times the potential difference between these 2 points. The final point was B, so we have written VB minus VA. This VB minus VA we can write as delta V. So the external work done, W external, is equal to Q times delta V. And this external work is nothing but a change in potential energy. If charge Q is taken from A to B, where points A and B lie in electric field, regions of electric field, then the potential energy changes by an amount delta U, which is equal to W external, which is equal to Q times delta V. Having revised again what we have discussed till now, let us proceed to discuss some more things pertaining to these topics. Let's see a question. If electric field in a region varies as E is equal to some constant A upon R square times R cap, where r is the position vector, r vector is position vector of a point from origin, then you have to write an expression for potential in this particular region. Electric field is given to you and you have to write an expression for potential at some point whose position vector is r vector. So you know students, if you know the electric field, the potential is given by the formula minus integration of E vector dot dr vector from reference point infinity to the given location which we write as r vector. Now r vector is the location of that point, so that distance is r. So E dot dr. Now you see this expression how we write. E vector is this much. It is a upon r square r cap. Now what is the meaning of this? That if this is our origin, this is a point, this is r vector, then electric field at this point is directed along r vector. In this direction, the unit vector they have written as r cap. The E vector is written as a by r square r cap. Dr is displacement vector, that we can write as dr is the value and direction will be how much? R cap. Directly also you could have written E vector and dr vector are in the same direction, so it becomes E into dr into cos 0, or you can write it in this fashion also. So minus integration from infinity to r. Now r cap dot r cap. Now this is unit vector, this is also unit vector. So r cap dot r cap must be 1, just as we have I cap dot I cap is equal to 1. So what will be left behind? Minus a is constant, that will come out, integration of dr upon r square from infinity to r. This minus I can take it inside, or you can write directly also. Integration of dr by minus r square is 1 by r. If you are having trouble in this, you can write the integration dr by r square first, then that minus sign and this minus sign will become plus. And the limits from infinity to r, so this becomes a into 1 by r minus 1 by infinity, this becomes 0 and the formula becomes a upon r. So our answer becomes potential at position whose location is r vector, point whose location is r vector is a upon r if electric field is given by this particular formula. So I just did this question to give you a sense of thinking that if electric field in a region is given, you can find the potential in that particular region. And if you see carefully, actually you already know these two relations. These two are the potentials and electric field due to a point charge. Due to a point charge, if you remember, suppose there is a point charge, the value of electric field at some distance r was given by E is equal to 1 by 4 pi epsilon naught times q upon r square. Now this quantity is a constant, that constant has been written as a, so by r square, and if you write in vector notation it becomes r cap, and the potential how much you know, 1 by 4 pi epsilon naught times q by r. If you see these two constants are same, 1 by 4 pi epsilon naught times q, here it was 1 by r square, here it is 1 by r. That's why here we have got for an electric field 1 by r square r cap variation, we have got a variation of 1 by r in potential. Let us see one more question. In this second question, there is an equilateral triangle of side A each. There is a point charge capital Q placed at the vertex B. An external agent, what it does, it takes point charge Q from point C to point A. So point charge Q is taken from C to A by an external agent. You have to find the external work done by that external agent. So to find the external work done, we shall apply the concept that the external work in carrying a charge from one point to another in a region of electric field is given by the formula W external is equal to the charge which you are carrying. You are carrying which charge? Q times potential difference between those 2 points. It is taken from C initial point to A final point. So we will write V at final point A minus initial point C's potential. Now if you see carefully, since this triangle is equilateral, what is the formula for potential at C and potential at A? Potential at C will be 1 by 4 pi epsilon naught times this charge Q upon this distance A. Potential at A is also 1 by 4 pi epsilon naught times this charge Q upon that distance, that is A. So are not they equal? And since they are equal, this difference becomes 0, and that's why the answer is 0. That means no external work would be needed to take the point charge Q from C to A. Let's see one more question. This next question which I will discuss is from your NCERT textbook, students. This is example 2.4. There is a square of each side D. 4 charges plus Q minus Q plus Q minus Q are placed at the vertices. First question that is asked is that you have to find the work required to put together this arrangement. That means initially if these charges are very far, one by one you have to bring these charges to their respective positions. How much work is to be done? By definition, this is nothing but the external work which you have to do is equal to potential energy of this particular charge configuration. Actually, work done should be change in potential energy. So final minus initial, we assume that initially they are at infinite separation, so initial potential energy becomes 0. So potential energy for this particular set of 4 charges. Now for a pair of charge, 1 by 4 pi epsilon naught Q1 Q2 by separation is the formula for potential energy. So this work done is equal to potential energy of how many pairs of charges over here? How many point charges are there? 4. So how many pairs can be formed? 6. First pair, second pair, third pair, fourth pair, and the fifth and the sixth pairs will be along the diagonals. So the formula will be 1 by 4 pi epsilon naught. First pair will be this one. So Q into minus Q will become minus Q square upon this distance, that is D. Second pair again we will have same thing. Again minus Q plus Q. Product will become minus Q square. Separation is D. Likewise this pair and this pair. For all these 4 pairs we will have same expression. So what I can do? I can multiply this by 4. Then 2 terms are remaining diagonal wise. So for that there will be 2 terms which will be identical. So I multiply by 2. Now I write the expression for potential energy of this pair. That will be 1 by 4 pi epsilon naught product of charges Q square. Even if you take this, it will be minus Q into minus Q, that is Q square upon. What is this distance? This is diagonal of the square. Using Pythagoras theorem you can find this is D, this is D, this will be root 2 times D. So the work done will be equal to this much. You can take this common and you can solve it out. You can simplify it further. I am not doing that. So that is the answer to this particular question. Second part, what they are asking, you have to find the extra work to be done to bring some charge Q naught from infinity of course to center E of the square. Now suppose this charge configuration is given and I take a charge Q naught and I bring it from very far distance to the center E. Then the question they are asking is that you have to find the work done. So how should we find the work done? The work done will be then given as, you have to find the external work done. Which charge you are bringing? You are bringing charge Q naught. So I will write Q naught times potential difference between those 2 points. So potential at point E, that is final potential, minus initial potential at infinity. Potential at infinity, how much we take, students? That we take as 0. So this gives you the formula, that is Q naught times VE. Now what is VE? VE is the potential at E. What is the formula for potential due to a point charge? Potential due to a point charge is given by the formula 1 by 4 pi epsilon naught times that charge by the distance of the point from that charge. Now here the potential is due to these 4 charges. If you see carefully, This is positive, this is negative, again positive, again negative. So the total potential at this point E will be 1 by 4 pi epsilon naught plus Q upon this distance. Let this distance be x. This will also be x. This will be x. This will be x. How much will be x? X is this distance. X is half of the diagonal. Diagonal was root 2d. So x will be root 2d by 2. But no need to find. Why? It will become clear. So the first term will be q by x. Second term will be minus q upon x. Third term will be plus q upon x. And fourth term will be minus q upon x. So if you see carefully, two of the terms are positive, two of the terms are negative. That's why they will cancel, and the total work that is needed to be done will be how much, students? That will be 0. I hope this solution is clear to you. So please try to practice them in your notebooks. Consider this next question. In this question it is given that there is a cube of side B. So all the sides, all the edges are B. Charge Q, 8 point charges, Q each are placed at its vertices. You have to find the electrostatic potential V and electric field at the center of this particular cube. How to find electrostatic potential? See, it is scalar quantity. Just add the potentials for all the charges at the center. Now what is the distance of each of these point charges from the center? That is equal to, so distance, if I write it as d, distance of this point from the charge is half the diagonal of the cube. Half times diagonal. I am not writing the complete language, students. You should write it yourself. Now what is the diagonal of a cube whose edge is b? You know that is root 3 times the edge. This is the diagonal. Therefore d will become how much? Half of this, that is root 3 upon 2. Thus the total potential V at the center is the point O, will be equal to sum of the potentials due to the individual charges due to one of the charges, say Q. So this distance is how much? This distance is equal to root 3b by 2, which we have written as d. So 1 by 4 pi epsilon naught multiplied by that charge divided by this distance. This distance is how much? Root 3b upon 2. Now this is the potential due to one of the charges, but there are how many charges? 8. So you have to multiply this entire expression with 8 to get the net potential. Simplification you can do it yourself. So this is first part of the question. Second part, what they are asking is the electric field. Now electric field also you have to add the contributions due to each of the charge, but the only difference is that this was scalar potential, whereas electric field is vector. So you have to do vector addition. Now it's clear that because of symmetry, O is at equal distance from all the charges, so the value of electric field due to each of the charges must be same. And they consider the diagonal. For example, this and this two charges, this is the diagonal of the cube, and O will be at the midpoint. So this charge will create electric field away from it if it is positively charged, like so, and this charge will create electric field opposite to away from it, like so. So these two electric fields will cancel each other. Likewise, this charge and this charge, if you join them, will get the diagonal, and O will be at the midpoint of that diagonal. So their electric fields will also cancel. Likewise, this charge and this charge, their electric fields will also cancel. So each of the diagonally opposite charge produce electric field of same magnitude but opposite direction. You write that reason, and therefore by symmetry we say the net electric field at center of that Q will be how much? It will be 0. Next question I am taking from H.C. Verma, page 123, question number 53. A uniform electric field of 10 Newton per coulomb exists in vertically downward direction, which I have represented by the red arrow pointing downward. So this is uniform electric field, that's why I have drawn parallel lines which are equally spaced. So this is E vector. You have to find increase in electrostatic potential as one goes up through a height of 50 centimeter. Some agent, some person goes up. If you move from point A to point B in upward direction through a distance of 50 centimeter, you have to find by how much will the electric potential increase. So you have to find change in electric potential delta V. If this change is positive, you will say it has increased, and if this change is negative, that means potential has decreased. So delta V you already know, students. You are moving from A to B, so this is nothing but VB minus VA, and that is nothing but negative of integration E dot dr from initial point A to final point B. Now if you choose a small displacement dr vector, which I have shown by this particular arrow, this black portion, this small displacement dr is in upward direction. I choose this point as suppose origin, and I am moving in upward direction. This is our x-axis, so I take this as our x-axis. So this distance is 50 centimeter. So our displacement dr vector and E vector are in opposite direction. That's why this becomes E times dr times cos 180 degree, and the integration is from A to B. What is cos 180? Minus 1. That minus and this minus will become plus. So it becomes simply E dot E into dr. But E is uniform given in the question. So it is constant, so it can be taken out. Now what we are left with is this. Now what is integration dr from A to B? Integration dr from A to B is nothing but the length of this particular line AB, which is x is equal to 50 centimeter. So this value is nothing but 50 centimeter, and E value is how much? 10 newtons per coulomb. So their product is our answer. So 50 centimeter can be written as 50 by 100 meters. So this is in SI system. In SI system, the delta V will have a unit of volts, or you can write joule per coulomb, and the value will become how much? You can see 1 0 will cancel, 1 0 will cancel. We are left with 5 volt, and the answer is positive. That means the potential has increased. That's why the change is positive. Okay students, I'll stop here. I suggest you to do some numericals on potential energy, difference in potentials and electric field. See you in the next class.